Okay, here we go. So we want to talk about lines in space. So let's just review lines in R2. Oh, this again. Let's hope this is the end of my battles with technology. Here we go. This is the end. So let's talk about lines in R2. So if I had a point, if I was given a point, one other thing would I need to then describe this set of points that make a line through that point. Right? So given a point, what would define a line through that point? What other information would I need about the line?
Another point the line goes through.
Okay, that would work. And then because those 2 points could tell me what about the line? Yeah, let's be more profound though. Rate of change, right? Rate of change. So given a rate of change plus a point, would you agree that that determines a unique set of points, a unique line? Right? If we had the rate of change and a point, there would only be one line that would go through that point with that rate of change. Okay, so in R3, it's something similar, so we'll start with a point here. But we're not really ready to talk about rate of change in R3 yet. We will, but not quite yet. So what is something else that I could have along with that point that would define a unique set of points that would, or a unique line? Anything else we've been talking about recently that might, with a point? What about a point and a vector? Right, because a vector would point in a direction, right? So, yeah, so a point and a vector can define a line for us. So here's the point 3, negative 3, 2. So I'm gonna put a vector in standard position with that vector 3, negative 3, 2. Okay, and that will give me that point 3, negative 3, 2. Right, if I put it in standard position, then the components of the vector are the same as the location in space, right? We've talked about that. Okay, and then I'm going to use this vector then to determine what line I'm going to create from that point. So I'm going to put it with its tail at the tip of that first one. So that's blue. So I'll go blue here. So that's the vector. Negative 1, 2, 1. And so we actually just found another point on the line. How did I just find another point on the line? Or how would I get that new point on the line? What would it be? What's that? He wants to add the 2 vectors that we're going to say. If we add those 2 vectors together, then we'd have a new point on the line, and it'd be this one here. And I'm going to also make that point as a position vector. So my new point, and what would that new point on the line be? I'll write it as position vector. What is this second point that I've now found on my line? 2, negative 1, 3. Okay, so that's this one. Okay, now I want to get still a third point on the line. What could I do now to get another point on this line? So it's through 3, negative 3, 2, according to this direction, negative 1, 2, 1. So that gave us a new point 2, negative 1, 3. So how could I generate another point? What's that? What do you mean? Which is the previous vector? So you want to take this one and make a copy of it and do it again. So what's another way to think of that? So instead of instead of including a new vector on there, how can I just adjust this one to get that same result?
Multiply by scalar.
Harrison,
Add it to the red one.
what's that?
Add it to the red one and multiply the scalar.
Yeah, so instead of I could take the blue one and just put it again, or I could just take the blue one and do what? Scale it by 2, right? So if I scale it by 2, it's going to give me another point on the line. And so this is how we're going to generate all the points on the line. We're going to scale that blue vector. If we scale that blue vector by any real number, you see that it will give us every point on the line. Should make sense. Ooh. Okay. So then I take every scalar multiple of the blue vector and add it to the black vector, my initial point. Then I'm going to get every point on the line. Okay. So let's do that a few times here. So that's how we generate points. Over here. So that first point, and then we'll use t to be our scalar. So we can have t. And so for that first point, so what's the scalar on for that first point that we got? That one right there. What would the scalar t be? 1. And the second point we talked about was 2. And so then let's do something original here. How about -4? All right, and then 100. Okay, and so then when t is 1, we start with the point 3, -3, 2. And then we add what? 1 times the blue vector, which was -1, 2, 1. To get, that was our 2, -1, 3. See how this works? So for 2, we would start with same point, and then add, what do we add now? 2 times and we're going to call this the direction vector, right? Because it points in the direction of the line, or is parallel to the line, right? The direction vector is parallel to the line. And what point will we generate then? So let's show that here. So here's that second point right there. And what point is that? I heard 114. Is it right? So this is the point 2, -1, 3, then 114, and then how about -4? What does that give us? 7? Did I hear that right?
So it's 7, -11, and then
I just
-2, sorry.
we good now?
The second one's a negative number.
How about now?
Yep.
7, -11, -2. Oh, so you understand that to generate points, you just pick a different t. You just scale that. Positive will go up to the right, negative down to the left. By scaling it for every t vector, you generate every point on the line. Okay, so we don't have to do 100. So what's generally going on here? We're going to start with our point, so we'll call that P naught. And then we're going to add some scalar times our direction vector, which I'll just also call V. And that will generate every point on the line. So our P naught is X naught, Y naught, Z naught. And is that fixed or varying? That's fixed. What about T? Fixed or varying? We vary T. V, so the direction of the line, we'll often call it A, B, C. Fixed or varying? Right, so that's fixed. And then P is X, Y, Z. Fixed or varying? Every point on the line. So for different values of T, generate different points on the line. So those are your varying quantities in this. So that's our equation of the line of space. It should make perfect sense, right? It's not something you just memorize and just use to solve problems. It should make perfect sense. You start with some points, you've got some direction, and you're going to throw that direction vector at the tip of your point, and then scale it, and you'll generate every point, right? It should make perfect sense. Okay, so now let's do the math on the right-hand side. So x, y, z. I'm going to change it around. So x, y, z equals. Now let's do the math. Do the math on the right-hand side. X, y, z equals what? What's the x component if you do the math? X naught plus TA. Then should make sense, right? Which means that the x point, or the x coordinate of every point on the line is x naught plus TA, right? And y is? Z is? So here's a different way. So this set of equations is totally equivalent to this vector equation. So this is the vector form of a line. Oh, no, sorry. No, not that. This down here. Vector form is the every point as a position vector equals the fixed point plus t times the direction vector. That's the vector form. So now we've gotten rid of all the vectors and we're writing it as 3 separate equations. And that should look familiar from Calc 2. What kind of set of equations is that? Remember this from Calc 2? Familiar? What was that called? Parametric function, right? Parametric function. So this is parametric form. Remember, you generated coordinates one at a time by some invisible input variable, right? The t. So it's called parametric form. Is that our? It's not our classroom. So we got the vector form of a line and the parametric form. Totally equivalent mathematically, just 2 different ways to express equation of the line.
Yeah, I have to go through.
Okay, so we've got our line here. It's kind of greenish gold. So question is the point 10, -8, -1 on our line? Is 10, -8, -1 on the line? See if you can figure it out. So think and talk if you need to. Is 10, -8, -1 on the line? Oh, so we never wrote. So you might start by, let's write this line. Write the equation of this line in vector form and parametric form. So we never really did that, right? So we just found examples, but we never wrote this particular line in parametric form and in vector form. And that goes back to identifying what's changing and what's being constant, right? So what's changing and what's constant for our particular line, that means you can write it in vector form. So, and then once we do that, then we can answer this question. So anyone want to tell me vector form? What is vector form of this particular line? Right, so this is a vector form of any line. So what's the vector form of our line that we were working on there? Yes, please.
It's 3, 3, 2 plus t, 1, 2, 1.
And then over here, we're going to say that equals what?
The line.
The line is an object. What is this? This is really generating what about the line? What does it generate? What's that? Yeah, the vector xyz, meaning every point on the line, right? So given a t, it'll crank out a vector that's pointing at a point on the line, right? And then our parametric form is x equals 3 plus, or 3 minus 2, we say 3 minus t. Y equals -3 plus 2t. Z is 2 plus t. Very good. Okay, so that's our particular line that we worked on. So now, is 10, -8, -1 on the line? Anyone think they answered that? Somebody else? Is it on the line? Yes or no? Yeah.
No.
Why not?
I just plugged in 10 for x, y for, or -8 for y, and then -1 for z.
Okay.
And see if all the t's are exactly the same.
Okay, good. So what is it? A value of t will generate points on the line, right? So now we're going backwards. We're saying we're going to check a certain point to see if there's a single t that gives you that x, y, and z. So you do that. So 10 equals 3 minus t gives t equals what? -7. So that means -7 better give us y as -8 and z as -1, does it? No. So t in -7 gives -17 and -5. Is that right? Conclusion? Definitely not on the line, right? A single t would have to give us that x, y, and z coordinate. Okay, questions so far? All right, how about this? Make some room for me here. What about this line? Violet, that's pretty. Okay, how about XYZ equals 1, 1, 4 plus 4, negative 2, 6, t times, shoot, plus t times 4, negative 2, 6. So xyz equals 1, 1, 4 plus t times 4, negative 2, 6. No. No world. I'm thinking. It's not even close. Negative 2, 4, negative 2, 4, 2. That's what I meant. So what do you notice about this line? So what about the point 1, 1, 4? Notice anything about that point? It was on our previous line, right? And what about the direction vector, negative 2, 4, 2? What's that, Harrison? I can't quite hear you. It's so loud up there. Yeah, so a scalar of the vector we already used, what about its direction? Same direction. So what about this line? Same line. How many ways can you write a line? Yeah, not only can you choose this initial point could be any point on your line, but also this vector could be what? Any vector, not any vector, any scalar multiple of this vector. And so choose that, choose any point that's on this line and any scalar multiple of our original direction vector, you get the same set of points, just for different t, right? Different t's are going to generate the points differently. So you gotta be careful for that. So just because I have a different point and a different direction vector, you could be writing the exact same set of points, same line. Okay, that's enough of me talking. Negative 9, negative 6, 18 here. So you had the same direction vector? Okay, does it work? Okay, how's number 4 going? Can I erase what I wrote? Can I erase it? Okay, so for number 4, it's pretty easy to check for same or parallel. Why? Same or parallel? Which vector? It's called the direction vector. Yep. So the direction vector for this one is?
2, -1,
3. Okay. The direction vector for this is?
4, -2, 5.
So what would it mean if these lines were the same line, same set of points, or parallel lines?
The first one times some value, so t equals that.
Yeah, one would have to be a scalar multiple of the other. Is it true? Nope. So boom, right off the bat, we can just go eliminate those. So then intersecting, so do you know what skew lines are? Does that make sense? So here's our skew lines. The corner edge up there, see the corner edge of our room up there? And this bottom corner edge of the floor in front. Are those parallel? Do they intersect? That's what skew is. They're not parallel, but they don't intersect. So that line across the corner of our room up there, it's got to ignore the pop outs. and then this front line here down on the bottom. They're not parallel, but they miss. So what would have to be true, say, if they were intersecting? Yeah, so right, there'd be a common point on both these. And would the same T and S generate that point? Would they have to? No. So it's not going to be that like the same number T as S is going to generate our intersecting point. It could be totally different numbers. That's why you got to keep it as T and S. If you put T in here and treat it as the same T for both lines, it messes everything up. It messes everything up. Because it's like you're trying to force the same value of your parameter to give you the same points, and that's not necessarily the case. All right, so how are we going to see if there's a point in common here? What can we do? If there's a point in common, then x values are equal, right? Or there's some t and s that give us the same x value, right? And that same t and s would do what? Give the same y value. So look what we got. Two variables, two equations, and we can get t and s from that any way you want, right? So matrix method, substitution, elimination. Did anybody do that? Anybody combine the first two and get what was x and y, or t and s? T was 1.
I didn't do it though.
Anyone do this?
I did the bottom.
Anyone do the top two? You did the bottom two?
Yeah.
You said y is equal and z is equal?
Yeah.
That's fine. Perfectly great. So let's do that. We're going to set the y is equal and the z is equal. And you did the math, and what'd you get?
S is 0, T is 1.
Perfect. So 1 plus 3t equals 4 plus 5s. That's our z's. This is our y's. And when you combine those, you got t was 1, s is 0. Let's just check that. When t is 1, you get 4 equals 4, and you get 3 equals 3. Perfect. So to get the z and y's to be the same, you have t equals 1 and s equals 0. And I've skipped all the math, right? I've skipped all the math, solving two equations, two variables. And so then what else needs to be true? For that t and that s, we have to get same x. So now here's the big question. When t equals 1, you get x equals 5. And when s equals 0, you get 1. Conclusion? Do they intersect? No. They do not intersect, right? So when you get the same y and z coordinates, x's miss. The x on the first, the L1 is 5, and the x on the second is 1. And how would you know they intersected? You got the same x value. So now you have a t and an s that generate the exact same point. Now you have intersecting lines. If they weren't the same line, right? Right? If they weren't the same. Okay, so you got the written